All right, now that we talked about some of the theorems related to trapezoids, whether isosceles or regular trapezoids, we're going to apply some of our coordinate geometry formulas that we've used throughout the unit and our work in geometry previously in other units, and prove if this is a trapezoid or isosceles trapezoid. So we have a quadrilateral ABCD with the given vertices, show that it is a trapezoid, and determine whether it is isosceles. So let's see. If we're going to show that it's a trapezoid, well, we know by definition that we have to have one pair of parallel sides. We know we can use slope to figure that out, and since we have it graphed here, we can really do a little rise over run and do that. I'm just going to review, though, the slope formula with at least one of these sides, because we've used that, and if we didn't have the graph there, you probably would use that. So let's go ahead and do the slope of AD, and then we'll do the slope of BC. Recall that the slope formula is rise over run, but in coordinate form. So the difference between the y values at y2 minus y1 and the difference between the x values in the denominator, x2 minus x1. That's the slope. All right? So remember, it doesn't really matter which one you call the second one or the first one. Since I wrote it y2 minus y1, if we're going to do AD, I guess I will do the second y value minus the first y value, even though that gives me a negative here. 0 minus 4, and then the second x value minus the first x value, negative 1 minus negative 3. So that gives me negative 4. Remember, negative 1 minus negative 3 is really the same as negative 1 plus 3, which is 2. And that reduces to negative 2 over 1, or negative 2. Now let's take a look at the slope of BC. Instead of doing the slope formula here, since we have the graph and I already did that slope formula once, let's just look at BC here. If we're going from B to C, we're going down 2, so negative 2 for our rise, and right 1, so positive 1 for our run. So negative 2 over 1, which is negative 2. So we can see that these are the same slope. So parallel. And if it's parallel, if we have one pair of parallel sides, then we know it is a trapezoid. So we know for sure it's a trapezoid. Now let's show whether it is an isosceles trapezoid or not. It kind of looks like it's isosceles. In other words, the legs AB and DC are congruent to each other, but let's see if it is in fact the case. Remember, to find the length, we basically do a little Pythagorean theorem work, and you could almost make a little right triangle over on the graph there. But a Pythagorean theorem in one step in coordinate form, remember, is the square root of x2 minus x1 squared plus y2 minus y1 squared. So it's basically the square root of a squared plus b squared, but in coordinate form, and this is what we call the distance formula. So AB distance, therefore, let's take a look at the difference between the x values. So I'm going to go second x minus the first x squared plus the difference between the y values, 5 minus 4 squared, is equal to, so 2 minus negative 3 would be 5. 5 squared is 25. 5 minus 4 is 1. 1 squared is 1. So square root of 26. So this has a distance of the square root of 26. It has that length. And then we are also going to get the distance between C and D. So once again, let's do a little bit of work here with the Pythagorean theorem distance formula. And so we're going to, lost the coordinates here, CD, we're going to take the second x minus the first x. So negative 1 minus 3 squared plus the second y minus the first y, so 0 minus 3 squared. All right, so negative 1 minus 3 is negative 4. Negative 4 squared is 16, plus 0 minus 3 is negative 3. Negative 3 squared is 9. Suppose I could have gotten both of these positive if I had reversed the subtraction, but in any case, get the same answer. Square root of 25. Okay, notice that those are really, really close to each other, but these are not equal. So we know that this is, although it is a trapezoid, it is not an isosceles trapezoid. So let's conclude on the bottom, or write a conclusion, write a justification. So it is a trapezoid since it has one pair of parallel sides. But it is not isosceles since the legs are not congruent. Oh, I might have phrased that a little bit differently if I had to redo, but oh well. Might say something like, but since the legs are not congruent, it's not isosceles. That might sound a little bit better. Okay, so we use coordinate geometry to go through and calculate the length of the sides and the slopes so we can identify what type of trapezoid it is. All right, so moving down in the next part here, we have a new term here, and it's something called the midsegment of a trapezoid. So midsegment of a trapezoid is the segment that connects the midpoints of the legs of the trapezoid. So here's a leg and a leg. You'll notice midpoints are marked. So here's midpoint, and then we have the other midpoint, and connect those, and we get something called the midsegment. Now, a midsegment of a trapezoid is a segment, of course, inside the trapezoid that has some other characteristics, and it has two that we're going to put into this one single theorem. The midsegment itself, you notice this trapezoid here, it's kind of tilted on its side, so BE is the midsegment. But you notice it is parallel to the two bases. So parallel to each base, and then it has a distance relationship. It is 1/2 of the sum of the lengths of the bases. Okay, so let's just think about that. Let's put some numbers on that to make this a little bit more clear. So let's say the bases have length 2 units and 8 units. Well, that would mean BE would be 1/2 of the sum, in other words, 1/2 of 2 plus 8, which is then 1/2 of 10, which of course is 5. So BE would be of length 5. So when we say 1/2 the sum, really that's just a fancy way of saying the average of the two bases. Because there's only two bases, 1/2 of the sum indicates that same mathematical calculation. But since there's two bases, it's also the median of the two bases. So notice the median between 2 and 8 would also be 5. So that's kind of a quick, easy way. You can see the difference here is 3, the difference here is 3. So any of those can be really used to calculate the length of the midsegment. But 1/2 the sum is the theorem, and we're going to actually apply that down below here because we're given in the next problem the length of a midsegment, but only one of the bases. So we're going to say 1/2 of the sum, so 1/2 of x plus 18.2, 1/2 of the sum of the bases is going to be equal to the midsegment. All right, at this point you have a few mathematical options for how you solve this algebraically. One is you could use the distributive property. One is that you could multiply both sides by the reciprocal of 2, or sorry, reciprocal of 1/2, which is 2. You can divide both sides by 1/2. I think the cleanest, easiest way is probably to multiply both sides by 2 here, but you certainly could do the distributive property. You get some decimals in there, which we might end up having anyway, but in any case, I'm going to multiply both sides by 2. All right, so that cancels out. The 2 times 1/2 is 1, so that cancels out. So we're left with x plus 18.2 is equal to 15 times 2, which is 30. And then simple subtraction, undo addition by subtracting. So subtracting both sides, 18.2 from both sides, we get x is equal to 30 minus 18.2, which would be 11.8. So 11.8 is this here. And that is using that formula, but you may have noticed, well, this right here is a difference of 3.2. So 15 plus 3.2 is 18.2. So what if I went down by 3.2? Well, that gives me 11.8. So you can see that's almost a quicker, easier way of doing it. So give me a couple options there, but in any case, x is equal to 11.8.